Today we are going to talk about linear relationships. Let me just adjust my jacket because I can. Cool. Also, yes, I am wearing a green shirt under this, so that's going to be fun for. So if you have no idea what color my shirt is, because it looks like it's been cut out because it was green. But yeah, let's dive in. We're going to talk about nonlinear relationships. And we'll start with model checking. So let's import our French painting data, where we have 3,000 plus observations and 61 variables. Now, we've been fitting linear models, which effectively assumes that there's some kind of linear relationship between our explanatory and response variables. But how do we assess this? Well, we apply it. We look at the residuals to see if all that's left is just random noise, or if we have missed some fundamental structure. Because the idea is that our errors should be evenly distributed and have very little structure. Now, here's the code to create this plot, where I extracted the residuals from the fitted data. You can see here. And all it is a function of mapping the relationship of height as a function of width. And I've plotted the fitted versus the residuals and plotted it all. And here's some extra detail. Frankly, the detail that it's a good amount of detail, but it probably didn't need to be on its own slide because it's showing us the discrepancy between the estimated model and the observed model result for each item. So a little more on Augment. So what Augment does is it gives you all that underlying stuff that we tend to look at with models. There are 9 just columns, and it spits out all the data, both the observed and fitted, along with the residual, the prediction, the variance. It's got some nice little stuff in there. So I encourage you to check it out. Now, for residuals, what we are looking for is residuals that are randomly positioned around 0 with no visible pattern along either the X or Y axis. What we want is just bleh. We want indistinguishable, just gray smudges. This is pretty decent, although it's a little more it's a little longer than I would like, but that's more of a product of how it's plotted. So just to be clear, this is good. There's not a lot of pattern. It's a little denser in the middle, which is what we would expect with everything kind of normally distributed across the axes. What we don't want is structure, like this fan shape, where we have very little residual variance at all at lower levels of our predicted values, but we have way more residual at higher levels. We've got this fan. We don't want to see this. I mean, if we have this underlying structure, it's good to see it. Ideally, we wouldn't see it because it's not there. That makes sense. So look at your data, listen to it. It will tell you many important things. Like in this plot, that we have a problem. Also, problem. Here, we've got clear groups where their shape. This looks like a flag. We're also not looking for correlated values. So here we have shape. I know this looks very similar to this horizontal tube thing, but here we have tilt. We have structure built in. We could fit a line to this data, and have that line be included in our model. There's something that explains this shape. So we are missing. This plot clearly indicates that we are missing a variable. But any pattern, including nonlinear. So this very clear shape. It's the arch from St. Louis. All right, maybe. But if you can see something, and we're not talking like fuzzy Rorschach ink blot, there's residual here that needs to be modeled. So let's take a look at this plot. What patterns does the residual plot reveal that should make us question whether or not a linear model is a good fit for modeling the relationship between height and width of paintings? Well, in case you hadn't been paying attention, we'd already been kind of hinting at what kind of stuff we want, like maybe it'd be good to model in a grouping variable because there seems to be structure here. It looks like there are, like it fans out, so we already know that's bad, but the fanning seems to be in two distinct chunks. So there's structure here, which tells us we need to go back to our model and think about what else we have, because we have variables we can include to model some of this structure out. All right, so let's talk about exploring linearity. So remember how, again, we're using the Parisian data, just plotting the price as a function of number of paintings. This is not normal data. This is very skewed, where most paintings are cheap. And there are some that are really extreme out there in 30,000 money units. Now also, if we look at the relationship between price and width, well, there's also a lot of smushing, where most of the prices are really close to the bottom, but there are some really extreme ones as well. So let's focus, because we got a ton of data here. Let's just focus on where the bulk of it is. So width less than 100, just for our own sanity. So that, is effectively paintings that are narrower than 2.6 meters for our non-imperial units of measurement people. So it's still decent chunk. So we're going to filter our data and assign it to a new data set so that we can just play around with that little chunk. And that way we also don't have to keep typing in the filter piece every single time. This will save us some computation later because we only have to filter once instead of each time. Okay. So here, I've plotted this data two ways. One is plotting the relationship between price and width. We already did that one, right? Now, let's try a different way. I think I hinted at some of these linear transformations and things like that in earlier modules. And this is one of the key reasons why it's good to know about Tukey's ladder, because it gives us a good hint of where to start. And we can effectively start by taking the log transformation of our data, because what the log transform does is it spreads out data at the bottom of the scale and compresses it at the top, which can be very useful, especially when you have, well, very skewed data, because it spreads apart at the bottom and smushes together the top so that it fits in a nice range. Now, does this lead to kind of not so fun interpretation? Yeah. But, yeah, okay. So, just to kind of bring us back to the slides. So which plot shows residuals that are uncorrelated? So again, raw data on these two plots. Here we have the residuals. And they look very similar to our data structure, but I promise you that these are different plots. So here we have very clear structure. It almost looks like Manhattan, or something. There is very clear structure in this residual data when we have price as a function of width without any transformation, versus the residuals for the log. They center around 0. It's evenly balanced on both sides. Sure, there's kind of trailing off at the top, but there's much less structure here compared to non-logged. Okay, so we saw that price had a right-skewed distribution and that the relationship between price and width was nonlinear. So in these situations, a transformation is usually, well, useful. Even if you don't put it in your final model, just to get a sense of, is there a way to make this data look a little nicer? And it's not just for aesthetics, it's because model assumption violations. You really want your residuals to be uncorrelated at the end of the day. You want to extract all the structure you can, so you're just left with noise. So in order to decide which transformation to use, we should examine the baseline distribution of the response variable. So for extremely right-skewed data, one of my go-tos is the log transformation. And you can consult Tukey's ladder on this. I think I have course notes. There will very much eventually be a video just on Tukey's ladder. So yeah, so when I say log, I'm talking natural. Well, so there are two types. So there are two types. So log, and is a little different than natural log. So so the default for log is the natural log. Sorry, I'm just babbling at this point. So in this case, the log transformation is the natural log. It uses exponents. It's nice. It's very convenient. And you can see the default for the log function. So, okay, great. But this creates a new problem. What problem is that? How to interpret our results. Because logs are not something that we intuitively think in. I personally do not think in log transformations. You do you, but I don't do them. It's not my instinct. So yeah, no, they'll give us really nice estimates, but anyway, let me show you this linear regression. Okay, so here we have linear regression and we piped it into SetEngine, and we further piped that into fitting the log of price as a function of width, where our data is that restricted range width, and we've tidied that all up to give us a nice tibble. And what it tells us is that we have a mean, that's what the intercept is, as well as a meaningful slope coefficient. But let me talk about how to interpret these. So here's the model that we've generated. We've estimated the log price as a function of our intercept, so 4.67 plus 0.02 times our width. So for each additional inch the painting is wider, the log price of the painting is expected to be higher, on average by 0.02 livre. I don't know. By 0.02 money units, which is not a useful statement, because for many reasons, but primarily, what the hell does that? How is that helpful to us? When you increase in logs. Right. So here's how you work with logs. Just as a refresher, and how to subtract them. So log of A minus log of B equals log of A divided by B. Does this ring a bell? So with natural logs, e to the log of x equals x. So we can use these identities to undo the log transformation so we can interpret our coefficient in a meaningful way, or closer to meaningful way. So the slope coefficient for the log transform model is 0.0192, meaning that the log price difference between whose painting widths are 1 inch apart is predicted to be 0.02 log money units. Okay, so let's put that into plain English. So using this information in the property of logs, fill in the blanks in the following alternative interpretation of the slope. So for each additional inch of painting of width, the price of the painting is expected to be blank, on average by a factor of blank. Okay. Is this helpful? I'm doing the transformation. So I'm not going to spell this out for you because I think it is a good exercise to actually work through the data a little. Okay? So let's work through this code, or work through the math. So we can smush these together. So log the price of width plus x minus log the price of the width of x. X plus 1 minus log width of x minus 1. Then we can log that whole thing, combine them, which is beautiful. I love log. So now we have the log for the price of width x plus 1 divided by the price for width x plus 2. And that equals 0.02-ish. Now we can take the natural log of both those hot messes. So now the ratio of for width x, and have that be divided, the divisor of price for width x plus 1 is approximately 1.02. So for each additional inch the painting is wider, the price of the painting is expected to be higher on average by a factor of 1.02. Frankly, this is, I think, the easiest way to think about it. At least intuitively. Okay, so here's a recap, just so we can all orient ourselves. So non-constant variance is one of the most common model violations, but it is fixable by transforming the response variable often. The most common transformation when the response variable is right skewed is log transformation. You see this all the time with money. It's especially useful when the response variable is extremely rightly skewed because it pulls the compressed data at the right end closer to 0, or it pulls the data that is compressed apart and compresses that long tail. So it pulls and pushes in a way that is very helpful. So this transformation is really useful for variance stabilization. So when using a log transformation on a response variable, the interpretation of the slope changes. Just remember this. So for each unit increase in x, y is expected to be on average higher or lower by a factor of e to whatever our beta is. Another useful transformation is the square root. This is especially useful when response variables are a count. So transform or learn more. So data transformation may also be useful when the relationship is nonlinear. So however, in those cases, a polynomial regression or some kind of spline, or really, there are tons of other options, may be more appropriate. This kind of modeling is beyond the scope of our course, but you're welcome to try it out as a portfolio piece. Now, as an aside, what happens when y is 0? So in some cases, the value of a response variable might actually be 0. And spoilers, the log of 0 is negative infinity, which is a pain when it comes to modeling, because we can't really interpret negative infinities and put them in a model because it's just not reason, just can't. So here's the trick I use. So the trick is to add a very small number to the response variable in all these cases. So just shift everything by like a tiny little bit. So that way the log function can still be applied. For example, if we add 0.00001 to all our data, this will help our log. You have to do it for all of your data. I tend to just add 1 to everything, but it really depends on your unit of analysis. Because when you unscale it, you got to deal with that 1. So that is wrapping up this chunk on nonlinear modeling. I know I've just scratched the surface and it's more of a tease than actual like content, but there's a ton in this area. I encourage you to kind of check it out. I'll see y'all later. Bye. So today I am going to grab my hair stick because I forgot. This is going to be our cold opener. Cool, because we are modeling nonlinear relationships. You can see the magic that is the hair twist. All I do is grab and twist. Just prop it over. I'll prop it, but then I stab it. Oops, it's too tight. We're done.